If you want to master your NMR problem solving skills, then you are in the right place. Welcome to the NMR Challenges series, where each video presents a new NMR spectroscopy problem from beginner to advanced level. Here, we systematically analyze 1H and 13C NMR, along with 2D techniques such as COSY, NOSY, HSQC, and HMPC, depending upon the problem, to uncover organic structures step by step. So let's get started.
In this video, we have taken the problem from Pavia spectroscopy book, which is 4th edition, page number 221, and problem is 9. We have to determine the structure of compound having molecular formula C5H10O, and we have given the 13C NMR, depth 135 and depth 90 spectra along with 1H NMR. This problem looks very easy because we are seeing only 2 signals in 1H NMR and 3 signals in the carbon. But this is not true. Actually, this is a tricky problem, and you will see why I am saying like this. While solving this problem, we are going to learn how to calculate the index of hydrogen deficiency, how to interpret the 1H NMR and 30C NMR, how to analyze the advanced spectra like DEPT in this video, and systematically determining the structure of the compound. So first we will calculate the index of hydrogen deficiency. The formula is 2C plus 2 plus nitrogen minus hydrogen minus halogen divided by 2. So here are 2 multiplied by 5 carbons plus 2, 0 nitrogen minus 10 hydrogen, 0 halogen divided by 2, 12 minus 10 divided by 2. So it has 1 degree of unsaturation. Now look at the carbon NMR. There are 3 signals in the 13C carbon NMR. So it is better to write in this way so that you can properly visualize the things. So this is 26 ppm. Let's say this is 36 ppm and it is 84 ppm. And 3 signals indicates that the carbon has symmetry because there are actually 5 carbons, but you are seeing only 3 carbons in the NMR. So this means that 2 carbons are equivalent. Now, if you write depth 135, so in the depth 135, this signal is in the positive phase. So in the positive phase, we see the signals for the methyl or CH, methane carbon. Since it is at 26 ppm, which is in the shielded region, so we can say that this belongs to the methyl carbon. And there is no signal. So this means this signal belongs to the quaternary carbon, or we can say that the carbon which does not have any hydrogen. And 84, it is coming in the negative phase. Negative phase signals belongs to the CH2 carbon. Okay, now look at the depth 90. In the depth 90, this signal is missing, this is also missing, this is also missing. So it means this compound doesn't have any CH. Now we are going to interpret 1H NMR. In 1H NMR, we are seeing 2 signals. So 2 signals means there are 2 types of hydrogens. But the molecular formula has 10 hydrogens. So this clearly implies that the molecule has symmetry, plane of symmetry. I repeat, the molecule has plane of symmetry. Now the signal around 1.3 ppm, it is singlet and correspond to 6 hydrogens. So this is possible that there are 2 methyl groups and which doesn't have any neighboring hydrogens, or there are some equivalent hydrogens. So this is the possibility. So this one belongs to CH3. And the another signal which is coming around 4.4 ppm, which is quite deshielded, it is also singlet and corresponding to 4 hydrogens. So there is a possibility that this compound has 2 CH2 group. And this value indicates that this CH2 linked to the oxygen. And we can see that the oxygen is there in the molecular formula, right? So it means the compound has CH2 which is attached to the oxygen. So we can write like this. Now we have all these pieces of information that the compound has CH2O, methyl, 1 quaternary carbon, 1 degree of unsaturation, and we have to put all this information together. Now this is the crucial part because we have to carefully think all the possible structures and identify the one that is fully consistent with the molecular formula, index of hydrogen deficiency, and all the spectral data. Okay, so when I see the 1 degree of unsaturation, the first thing which comes into my mind is carbon double bond carbon of the alkene group. But when I write carbon double bond carbon, then I can satisfy the 1H NMR, because as you can see that there will be CH2 and CH3, which is going to show the uh, triplet and quadruplet, and there will be a alkene protons as well. So this cannot be the correct structure at all. Now, if you try to put ring, because ring also contribute for the 1 degree of unsaturation. So after putting this kind of 5-member ring, if I add methyl, then I am missing the quaternary carbon, because this is the tertiary carbon, and this methyl is going to show the doublet, and this hydrogen will show the multiplet. But in the 1H NMR, we have only 2 signals, right? So this can be the correct structure as well. What about if I make the 4-membered ring? Let me draw the 4-membered ring, and now we can put the methyl group, and you can put the oxygen here, but you cannot put the CH2 because already you put the 5 carbons. So let me make OH. Is it possible? No, because I don't see OH signal in the 1H NMR, but this compound has a plane of symmetry. So this gives me an idea that if I introduce this oxygen in the ring, then still I will have plane of symmetry of the molecule. Okay, this is the oxygen, and now I am putting the methyl group here, and I can add one more methyl group, as I know that in the compound there are 2 methyl groups. And now look at this compound has plane of symmetry, right? And this methyl and this methyl are equivalent, so let's call it A, and this is also A. And this one CH2 and this CH2 are also same type, so this is called, let's call B, and this is B type. Now let me assign all the carbon signals to this molecule if it is the correct structure. So this CH2 can be observed at 84 ppm because it is attached to the oxygen, and second reason, it is in the ring, so it can be deshielded, right? And what about this methyl? This methyl will come at 26 ppm, and now there is a quaternary carbon, and this quaternary carbon will go to the 36 ppm. Okay, this one compound is satisfying our the carbon NMR spectra. And how many carbon signals you can observe? 1, 2, 3, right? So this is satisfying our carbon NMR. What about the proton NMR? So let me draw this molecule again, and let's assign all the proton signal. So there are 2 signals in the proton, and let me check how many signals it will show. So one signal belongs to the methyl group and another signal will belongs to the CH2. Yes, so this compound is going to show only 2 signals in the 1H NMR, and this methyl will be around 1.3 ppm, right? And this CH2 attached to the oxygen, so for sure it will go to the deshielded around 4.2 ppm, and it will be singlet, and this will also be singlet. So this is satisfying our 1H NMR as well, and hence we can say that this is the correct structure for the given spectra.
So that's all for today. I hope this video helped to strengthen your NMR skills. Keep practicing because mastery comes with consistency. And I will see you in the next video with the another exciting NMR challenge. Make sure to subscribe so you don't miss it. Till then, take care. Bye bye.